So that was the sign test. It's very simple and intuitive, very clear for understanding a non-parametric test for one sample median. The problem with sign test is that it actually has a small power. So it means that if you even have an effect, for example, you test if a river is contaminated, and it is indeed, but very often the sign test will not show you. You need a very big size of effect in order to see the contamination, for example. There is a better alternative, which is called Wilcoxon signed rank test. And you already seen that sign test doesn't use any ranks, it uses only the sign. And in this case, we are going to use ranks, okay? So the idea is following. So instead of the real distance between median and the values, we will use the ranks, okay? How far in terms of ranks the values are, okay? So that's the procedure. First of all, we start in the same way. We take a difference between the every value and the median. And then we order these values according to the absolute difference, so we don't care about the sign. And then we exclude all values where the difference is 0. So all values equal to median should be excluded. And then we recalculate. If indeed you have such values, you just reduce the number of the sample size using these values, okay? And then you assign a rank to each ordered value. So the first rank will be to the value with the smallest difference, the second rank to the next smallest, and so on. Then you assign a sign also to each observation using the difference, okay? Then you get a sum of ranks for values that are positive and sum of ranks for values that are negative. Think, it's very close to the sign test, but in the sign test we just calculate it, we just take all pluses and sum them up, all minuses and sum them up. In this case, we take all pluses and we sum up ranks for these pluses, and then we take all minuses and we sum up ranks for the minuses. So it means that we will take into account how far the values are from the median, okay? And then we calculate a statistic, which just is smallest, like it did in the sign test. It's just the smallest of these two values, and use these statistics to get a p-value, okay? Maybe it looks a bit more difficult. I'm going to show you an example in a second. So we use the same case study, river. So the first step is to take a difference. So we have a differences here, okay? So you can see that, for example, the smallest difference, we do not take into account sign. It's minus 4.2, this one, right? And that's why it has a rank 1. The next smallest difference is minus 5.1, and it has rank 2. The next smallest difference is minus 5.4, and then it has rank 3, and so on. So we just continue until we define all the ranks. And then we also make so these are ranks, then also make a column with signs, okay? So see, this difference is positive, so the sign is plus, okay? This difference is negative, so the sign is minus, okay? So we have ranks and signs, okay? Signs look the same as in sign tests, and ranks, of course, it's something new here. Then look, take all pluses, so we have plus here, and we have plus here, right? Then sum up the ranks. So in this case, we have 6 plus 4, it's 10. Then take all minuses, and sum up the ranks. So in this case, the number of if we sum up all ranks for the pluses, it will be 10, and if we sum up all ranks for the minuses, it will be 45. Okay. Then the statistic W is just the smaller of these two values, and that's a 10. Okay, that's it. Now we need to know how this statistics is distributed, and in fact, it's distributed normally. Only if the number of values which are not equal to the median is at least 20. So most of the non-parametric methods needs at least 20 values, otherwise they will not work correctly. And then this is the distribution is normal, this is the average for the distribution, and this is the standard deviation for this distribution. And that's the z-value. Okay, so just calculate the z-value and then use the CDF function for normal distribution to calculate a p-value, corresponding p-value. And then you can see that actually the average value and the standard deviation depends only on the size of the sample size. So it's relatively simple. So if we do all calculations, the average value will be 27.5, the standard deviation will be 9.81. Okay, so we have the W value is 10. And 10 is, of course, quite extreme for 27.5, right? So it's by 17.5 smaller than the 27.5. So if you calculate a z-value, it will be minus 1.78. And you remember, for the normal distribution, if you have plus minus 2, it gives you 95.5. If you take plus minus 196, it's 95%. In this case, we have minus 1.78. So it seems like for the both tail test, the p-value will be larger than 0.05. And indeed, if we calculate it, it will be 0.074. So 7.4% chance to get a sample A we have, or even more extreme, if indeed the median chloride content in the whole river is 146. Okay. And now we just can compare the p-values for this particular example using a t-test, a parametric approach, and then Wilcoxon and sign test. Okay, and because indeed we can use a parametric approach here, so you can see that the p-value for t-test is 0.06, it's the smallest value. Then the Wilcoxon is a little bit larger, so it means that the Wilcoxon test has a little bit smaller power comparing to the test set. And the sign test has even larger, so it's 10.9, almost twice larger than the t-test. So indeed, sign test has the smallest power in this case. Okay. And then again, if you want to do it in R, there is a function, it's called Wilcox test, and this function is very similar to the t-test. You provide a sample, it's x, then you provide, it's called mu, but of course it should be median, okay? And then this exact equal to false, it's not necessary. You provide exact equal to false only if your sample size is below 20. In this case, of course, the results are not quite reliable, but at least you can do something. Okay. Then if you want to make a test for one tail, meaning for either this or this hypothesis, you just use the same parameter as we usually use. It's alternative either equal to greater or alternative equal to less. Okay.